Should be there. But I can start second half. So, the main source of examples carefully is what we call scalar manifold. And I would like to explain what are scalar manifolds and motivation for all of this. The first thing we need to do is recall the notion of the first thing we need to do of a complex vector space. But I'll write it in this way: a complex structure J on a real vector space V. So J is linear mapping with J squared equal minus the identity. And if you insist on writing the letter I, right, you think J of V equals I times V. But I don't. It's just an anti-evolution with J squared equal minus the identity. It follows that dimension, I emphasize where I am over R, this is even, and there exist bases, a basis, even many bases, but there exists a basis of V with J in that basis equal to I minus I. So this has already appeared in these lectures. This is called a linear complex structure on this real vector space. A complex vector space is a real vector space with a complex structure. There are many complex structures. That's the first thing. Second thing, recall the standard, the above in the first period, standard form of a symplectic structure. Above means in the first lecture. Namely, omega of VW in a good basis is V transpose J W. That's really dQdP. Note omega of JV JW well, we can all have fun because it's late in the afternoon and do this calculation and have fun and prove that we are really super geniuses. Equals V transpose J transpose J J W. Right. But as you know, J transpose is equal to minus I this. Right, that's the transpose of it. And this is J inverse. So this gets killed. And you see that what this is just omega of VW. It says that J preserves the complex structure, the symplectic structure. So in words, the complex structure J preserves the symplectic structure. Now, you have another idea on this thing. Define G of VW to be equal to omega J of VW. This was a good idea because you see this is V transpose J transpose, which is inverse, W, which is equal to V transpose W. That means by putting J in the complex structure in the first entry, you have a bilinear form, which is the standard bilinear form on the real vector space. This means that G is the standard positive definite. Bilinear form. Okay. Well, just for fun, let's write something which is related, and I will quote a friend of mine's father named Wigner, who's a physicist. He doesn't understand how mathematicians understood what is a Hermitian structure. Wigner wrote, if you read, he wrote on the unbelievable effectiveness of mathematics in the physical sciences. It's a very famous paper. And he doesn't understand, you can see in that paper, how could mathematicians discover Hermitian geometry, which is so important in physics, when you cannot see it physically? Yes? You cannot see the unitary group, you cannot see the standard Hermitian structures and so on. You cannot see that originally, and it came from mathematics. It's a very interesting thing. Well, let's look at this guy. H of VW equals G of VW. And now you have to learn to put the right sign in things. This is the right sign. By the way, let me just write this as it was. This is omega J of VW I omega J VW. Okay. So you have the real part of this thing is a positive definite bilinear form. The imaginary part of this thing is an alternating non-degenerate form. We put them together using a complex structure and you get a thing here, and let's check that it's Hermitian. Okay, Hermitian, all you need to check is H of W, well, I don't care which way you want to check it. Let's say what happens here. H of WV, let's make a check. What is this? H of WV is G of WV minus I of WV. Well, G is symmetric, and this thing is anti-symmetric. So this is H of V of W bar. And you can have fun impressing your friends at nighttime by checking that if you multiply the first thing by I, this comes out as I. And if you multiply the second thing by I, by the complex structure, well, obviously it comes out as minus I because of that. Okay. So what I've written down here are the axioms of a Hermitian structure. It is a statement in general now. If you have a let J be an omega tame, this is a modern word introduced by people in the last 20 or 30 years in symplectic geometry. So an omega tame complex structure or a symplectic vector space I haven't defined omega tame, so let me define it. It means what I just said, i.e. it's compatible and this thing that you get when you put J in the first entry is a positive definite bilinear form. Okay. It's perfect. Now I hope you know this is of course a Riemannian geometry, but I told you how important symplectic geometry is, but I hope you see that there is a very close connection between symplectic and Riemannian geometry if you have a complex structure. If you have a complex structure. It's more or less the same thing. If you have a Riemannian structure with a good complex structure, then I can recover the symplectic structure also. I can go backwards. You can go back and forth, and what you're really doing is you have this pairing, the Hermitian structure, the Riemannian structure, the symplectic structure. Given the symplectic structure, you build the Riemannian structure and the Hermitian. Given the Riemannian structure, you build the symplectic and the Hermitian. It doesn't matter. Yeah.
In this case, I is what? Is it J?
I is a number now.
Okay. So
Square root of -1.
So it's just a number. So if we have h of VW equals G, can you say minus, well, J times?
No, because, no, h of VW is a number.
Okay.
What does it mean, J of a number? It doesn't mean anything.
Okay.
Yeah, but I times, I mean, that's I in the complex numbers. You know, you have the complex numbers, then you fix a notion of I. You have a choice there, plus or minus I, right? You fix a notion of I, then you're finished. So in last semester, I fixed a notion of I, and that's that I.
Okay.
Now he has.
So suppose you have a metric, then you'd like to find the corresponding symplectic structure.
Yes.
So, does the J have to be this same J, or can it be something different? Or does it only have to satisfy that?
It satisfies the compatibility thing, and then you can define omega in an analogous way.
So what's compatibility? J squared?
J is an isometry of the metric, so G of JV, JW is G of JV, VW.
Mhm.
And then you can define the omega by just the same way I define,
Okay.
you go back.
It has to define also that J squared is equal to minus.
That's the key thing.
Okay, then, and that's all.
That's it.
Then, do we know for certain that J transpose times J is going to be identity? But that J transpose would be its inverse?
Oh, we know that J transpose is its inverse. Oh, it's a question, what does it mean, transpose?
Is it? Oh,
There are several notions of transpose going on here, so it's a little bit dangerous. But, okay, yeah, that's a good question. Yeah, but if you write down a basis, and you will see that J transpose is the,
it's always the inverse.
Yeah. yeah, it's a good question, because you understand what he's saying, transpose is somehow a metric related. Okay?
Okay.
Very good questions. Thank you very much. Okay, so we see this back and forth with symplectic and Riemannian, and this goes through Hermitian. And it uses the notion of a complex bundle. So, we are optimistic. 3, try it for manifolds. The symplectic manifold. Why not? Try the same thing. So, what does it mean? You should try J. Should be mapping. Well, at each point X in the manifold should be a mapping of the tangent space at X to the tangent space of X. Yeah? With J X squared equal minus the identity. So the tangent space should, that's the only vector space around here, and Darboux says in fact that is somehow good, can be realized. That should be this equation. So all X and varying smoothly in X. So in this lingo of bundles, this means that J is a bundle morphism of the tangent bundle of M with J squared equal minus the identity. Okay? And then you should require the requirements. So J is called, let me even write formally, definition, J is called megatane. If and only if two conditions are satisfied. Omega is an isometry of it really preserves the symplectic form. And if you hit the first thing with it, this is bilinear now. I can find that to be G, it's a bilinear form, and this thing should be positive definite, so it should be a Riemannian metric. Isn't that a reasonable thing? Okay. Of course, mathematicians have known this for a long time. And it's not difficult to prove, but I'll even call it a theorem. The space of omega tame complex structures on M is an infinite dimensional contractible manifold. There are many. Okay? So there are many. That's the first thing. You're looking, I mean, you're looking like you'd like to ask a question, no?
So looking at all complex structure determined by like different.
You give me omega, fixed.
Okay, so for fixed omega, all possible complex structures that you can build on M.
That's right.
Okay.
Yeah. Yeah. So omega, I meant to say it that way, yeah. Yeah, no.
And contractible fundamental group trivial.
Yeah, it's contractible, yeah, that's right. It's really, there is a strong deformation retract to a point. Okay, but it's infinite dimensional. Okay. Okay. Now I would like, I'm trying to tell you how beautiful mathematics is and how deep mathematics is. And I want to mention, I'm not trying to be your trainer and make you integrate 1 over x and get logarithm or something like this. I want you to see how beautiful and useful mathematics is. This kind of stuff here has been known for a long time. This is formal. But there's a very important mathematician of the living mathematician, and his basic works were in the second half of the 20th century. He's gone into mathematical biology now, and I'm sorry that he did. His name is Misha Gromov. He is, of course, from the Soviet Union and left the Soviet Union. He was in the group of a man, perhaps you don't know his name is Rokhlin. At the time it was called Leningrad, it's now called St. Petersburg. He produced very beautiful geometers, one of them being Gromov. Another is another friend of ours named Eliashkar. He's a professor at Stanford. Gromov is in Paris. I may be wrong about this date, but I just wanted to write a date, so I'll write plus minus. For me, that's not very long ago. I mean, you weren't born in 60, no, you weren't born for sure. But for me, it's not long ago. Yeah. He showed us how to use this space of almost complex structures to prove really deep and beautiful theorems. And he used these structures, he uses J, so let's put it this way, M omega J as above. To prove very deep theorems, deep results. I will just give you, this is non-trivial mathematics now, I will just give you a hint of what Gromov suggests and uses. Okay, just as a hint. Okay. Let S be a fixed Riemann surface, compact Riemann surface. what is a compact Riemann surface? I think most of you have experienced me in lectures. So it is a one-dimensional complex manifold, right? It's a one-dimensional complex manifold. So it is a one-dimensional complex manifold. One-dimensional complex manifold. This means that you have holomorphic coordinates. Z. I'm being a little bit pedantic, but you have holomorphic coordinates Z. If you have here, do you see any Z here? There is no Z here. Yeah? You have in each tangent, you have infinitesimal Z, because you have it in each tangent space. But you do not have coordinates for this. Okay? You do not have coordinates for, I'm going to talk about that in a minute. So here, here, J may or may not come from coordinates. What I mean by is coming from coordinates, what I mean by that is J of dx di equals dy doi, and J of dy di equals minus dx di, yes, where dz, where z or the coordinates zi is xi plus iyi. You get it? If you have coordinates, you can write down J. Right? Well, you see, that's J at the tangent space level. J of ddx is ddy, and J of ddy is minus ddx. It's rotation by 90 degrees in the positive oriented way. Right? That's, if you have coordinates, you have J. If you have J, you do not necessarily have coordinates. Okay? So these guys here, this infinite dimensional space, they're not necessarily coordinates. Okay. But here, for these things, I require coordinates. It's a surface, it's a Riemann surface. There are. Yeah.
One question maybe I should have asked a little earlier. So regarding this infinite dimensional contractible manifold, all the J's.
All possible J's, yes.
Why would it be infinite dimensional when, for instance, if we look, so W or omega itself, the form, is finite dimensional.
Well, don't forget, it's defined on each tangent space. So you're moving. I mean, in some sense, you have it's defined on every tangent space, an infinite many tangent spaces. Is that what you're thinking about?
So I'm thinking that since the dimension of M, so you have the dimension.
M is finite dimensional. Yeah.
Right, so it's
Two n dimensional.
Yes,
Or two n dimensional. Simplify.
right. So the dimension of all two forms is n squared. So two forms, regardless.
No, the space of two. What do you mean? What do you mean by that?
So,
Oh, you're saying, no, I've got it. You're saying that the module of two forms has a basis which is called dx I dy I, or something like this.
yes,
dx I1, dx I2.
and that would be n squared.
Yes, you're right, but Abik is saying it's a basis over what?
No, I mean, in general, the space of the omega plane complex structures, you're looking at the complex structures themselves. You don't care about like anything that sort of satisfies that.
Wait, before you get into that, let's start with his form, and then we get to what you're talking about, okay? He said the basis, and he's correct, for the two forms in a coordinate system, not globally by the way, but in a coordinate system, is dx I1 wedge dx I2, where we can assume that I1 is less than I2, right?
Yes.
What is the coefficient?
Oh, okay.
It's not a number.
C is into function.
The C infinity functions. So this is a finite dimensional module over the C infinity functions. It is not a finite dimensional vector
I
space.
see, okay.
So you have this immense variation from, that's what I started to say, you go from point to point to point, and these functions are varying. So you have this huge variation in the function, and you have the huge variation in these j's. So you can imagine how if you have one j, you can start to move it in many directions. It's very easy to imagine that, right? So it's in some sense, the key here is finding one such j, and then you start moving.
I see.
Okay? Okay, so we're doing that, and now we're looking at fixed surfaces, and now Gromov looks at the space. I'll use his language, in case you ever come across it, of pseudo-holomorphic curves of type S. In fancy language, we fix a homotopy class of the image space and look at mappings of S which are in that homotopy class. But I don't want to get into that, that's not an essential point here. Okay? So what does it mean pseudo-holomorphic? So phi of maps S into the manifold. Okay? That's a curve. Just a mapping. And phi star of J, and I'll emphasize J, the holomorphic structure on S, is J M of phi of V, star of V. Isn't that the definition of holomorphic? The differential is complex linear. Isn't that the definition of holomorphic? That's the definition of holomorphic. You weren't in my class. You should have been. You would have had fun. The definition of holomorphic is that at the tangential level, the mapping commutes with J. It means it's complex linear. Phi of I times V is, the tangent is I times phi of V, infinitesimal. It means it's complex linear. That's the definition of holomorphic. However, this thing here is only a structure in this sense. There are no coordinates, and so you have many of these things. Okay? These are called pseudo-holomorphic curves because the image complex structure doesn't have coordinates, and therefore, quite often we say almost complex structure. It's not necessary to say that, but that may or may not be coordinates. Okay? Yeah.
So what is J sub S and J sub M?
What is what?
J S and J M. Are they the same color?
JM, I talked about before. That's some
Complex structure on the manifold.
on the manifold. S is a Riemann surface. It's a complex manifold. It has holomorphic coordinates. If you have holomorphic coordinates, you have a J. Right? J of ddx is ddy. J of ddy is minus ddx. Are you okay with that? Okay? Yeah. Now this space is the key space to study. Let me emphasize something. If you start with a symplectic manifold here, and you are naive, and you say, I want to study functions from this manifold, to talk about this manifold. There is no such thing as a symplectic function. If you start with a symplectic manifold and think that you should talk about symplectic functions, yes, you're wrong. There's no real idea what that means. Okay? There's nothing that takes the manifold and goes to the numbers. So what Gromov said is, of course you're wrong. Instead of going from the manifold to the numbers, I'm going to map things into the manifold. They're two different things, going away from the manifold or going into the manifold. Now, Gromov is a differential geometer in theory. He knows about geodesics. They are curves into the manifold. So he's thinking here in some sense about what are the right holomorphic things which are parallel to geodesics here. Okay? Which are really, and he studies this space. Space of pseudo-holomorphic curves. Now, I hope I've whetted your appetite with his idea. Let me tell you one of his applications. You may find it trivial, but it is absolutely non-trivial. Okay? So, application of his ideas. Gromov ideas. Gromov himself, but I just Gromov's ideas. Okay. Let's go back to anything you physics people would be happy with. Let's go to R2n. Here's the manifold. So all this fancy business, let's go to R2n. If you read the work of Gromov, you will see that he's thinking in very small terms. He's found the right way to think about small things that will give him big things. For example, he thinks a lot about what is a triangle. He is not afraid to think what is a triangle. Maybe very abstract what is a triangle, but he's not afraid to think about what is a triangle. Let's look at this, and let's look at omega standard on this thing, which is dq dt. Okay? Okay. And now, let's look at a ball here. So I write a ball. This is a ball of equals the ball about the origin of radius, let's say of radius r, small r. This is a ball about the origin of radius small r. Okay? Right? So I'll draw a picture. Okay? This is typical Gromov. Oh, let's look at the ball of radius r. It was a beautiful little Russian accent. Consider the ball of radius r. And now let's consider a cylinder. Let's make a German cylinder. Z, the word in German for cylinder starts with cylinder. Starts with Z. The radius big R, the cylinder over, for example, the ball, the radius big R in R2. So, and this is the R2, for example, of the first variables here. So I hope you understand this. You have here is the R2 with the symplectic structure dq1, dq2, dp1. This is, so to speak, this axis here is 0. Here is this ball here, and here we have the cylinder over it. And here, the radius of the cylinder is bigger. You understand what I said? Take the yeah? Cylinder. Yeah. Okay.
So it has the same radius as the radius of...
No, big R and little r, so arbitrary operator. Okay? Big R and little r.
Okay.
Well, up here it looks confused.
What do you mean over?
Yeah.
Huh?
The same question. What do you mean by over? A cylinder over? So it's just a cylinder.
That's classical geometry language. A cylinder over something, you have a projection. The projection is just the projection on the first two coordinates. And so you pull back everything, So it's pre-image under the projection. I'm sorry, I use this classical language. This is a cylinder over something. I'm sorry, it's just my lack of language. Yeah.
So if the ball has, say, dimension 2, then the cylinder has dimension 3?
So as an example, let's do the dimensions. If we're in R, suppose the ambient space is R8, then all of these things are 8-dimensional. The ball has an 8-dimensional round ball, and the cylinder is over a disk of dimension 2, and with the pre-image, each fiber being R6. Yeah, because it's a projection of R8.
And you
I'm projecting on Q1, P1. If you don't like this thing here is Q2 equal through Qn equals 0, and P2 equals through Pn equals 0. Okay? That 2-dimension. Just project over that. Okay?
But how do you have a cylinder over the sphere? Because the
Over the disk.
So we are small, that's a sphere, and we are in the disk.
Both things are balls, but they're balls in different places. One is the ball of radius big R in the ambient symplectic space.
Yes.
The other thing is, I call it a disc, but it's a ball, it's just, okay? Okay? Yeah? And now, Gromov is interested also in geodesic. He's a geometry. He's interested in geodesic flow. So he's interested in Hamiltonian flows. So he's interested in, is it possible to take this ball of radius R here and flow, by the flow, can you flow it into the cylinder? You understand? You want to see what's happening under geodesic flow of geometric objects. Yes? So the question is there a symplectomorphism of R2n with a standard structure that maps the ball into the cylinder? Yeah? Is there a symplectomorphism which maps the ball into the cylinder? Let me just explicitly write the question. That's Gromov's question. It's typical Gromov. He finds something really non-trivial, but that you can understand, and then he finds some highly non-trivial method to solve it. So, is there a symplectomorphism phi of the ambient space so he's thinking in terms of Hamiltonian flows with phi of the ball R contained in the cylinder of radius R. It's a reasonable question. It's a question, how rigid is this symplectic geometry? And he's even telling you, maybe there's some invariance going on in here that we don't see. Okay? Anybody want to guess?
No.
You don't want to guess?
No, we're having this, no, again, so it's no.
Okay, but why did you raise your hand?
I want to guess.
You want to guess?
My guess is no, because, okay, so it might be a bit naive, but then, so if we can think of defoaming, so flowing the little areas of the, on the surface of the sphere and 2 areas on the surface of the cylinder, since that is a constant under the geodesic flow, of the Hamiltonian, then we should have equal areas, but in the cylinder it extends to infinity. So
Now this may be good intuition. He has some intuition about areas and invariants. This is, yeah, I like your intuition. Unfortunately, of course, it's trivially possible to do it if r is small enough. Little r is small enough. I purposely chose, I hope I chose the little r. Isn't it obvious that if little r is smaller than big R, then I can do it? Because translations are symplectomorphisms, I hope. Okay? Maybe you see something deeper, and the answer is if and only little r is smaller than bigger. And then you can easily do what?
That sounds like a triviality. It's like, well, if the
Why?
thing is smaller, you can always translate it if you sort of explain it that way.
It sounds, why does it does sound like a triviality, but why does it sound like it to you?
Because, well, you have this ball and you have the cylinder, and if the small r is less than big R, then you should be able to just translate it.
Yes, you can do that. I said if and only if.
Yes.
You can, if it's smaller than bigger, then of course you can do it.
But now the question is, can you do it for larger?
And the answer is no. That's the real question. And you would think you can take the ball and bring it in there. And you can do this with all sorts of structure-preserving mappings, but not with symplectomorphism. It's a very deep statement, and to prove this statement, Gromov introduced the space of pseudo-holomorphic curves in this method. Highly non-trivial, extremely beautiful, generated an entire epoch of mathematics, modern symplectic geometry. This paper, I think it's 1984. Prabha, do you have a question? No? Okay. So, yeah,
Are the symplectomorphism volume conserving?
they are volume preserving.
So that's why you can just shrink the ball.
You can, no, that's a very good, the first idea would be just to shrink the ball, right? But
The volume is not feasible.
why are they volume preserving? If you take the wedge product, the top wedge product of this two-fold, so the n-fold wedge product, it's just the usual volume form. So and it's something maybe related to what you're seeing. What you're seeing here is, of course, this is invariant. And that's what you were saying with area. But not only this, all these wedge products are invariant. And this is what Maria is talking about here. This is the top wedge product here. This is the volume form. So all of these things are invariant. So, I mean, and you begin to feel, okay, area is invariant, higher dimensional areas are invariant, and so on. Yeah. Well, this is a wonderful theorem, and this is the beginning of very deep symplectic geometry. Okay. I'd like to lecture a little bit more, and then we'll finish for today, okay? All right. You're exhausted. So we turn to a chapter is here, complex manifolds. Which have such structures. J. Which are omega 10. I convince you it's a very good idea to look at these complex structures. Yes? But what I mean by a complex manifold is with coordinates. So I mean with coordinates z1 through zn, and these coordinates z1 gives you ddxi, so zi equals x, oh this is terrible, zj equals xj plus I yj, and ddxj is mapped by j to ddyj, rotation by 90 degrees, ddyj is mapped by rotation to minus ddxj. Okay. Okay, that's a mega condition. Let me tell you, this is a mega condition. And let me tell you how to make that slang expression mega precise. Okay? And almost complex structure J comes from coordinates you're going to hate me, you hate me anyway, so you can just hate me even more. If and only if a certain tensor vanishes, it's called the nine-house tensor. The nine-house tensor of J is 0, and you apply that to two vector fields x and y, and this is, you see what happens when you take the bracket of x and y, and you compare that to this. There's really a logic behind this, but I don't want to get into it now. X, J, Y minus x, y vanishes for all x, y. X and y vector fields. In the manifold.
What is it called? Nine.
Okay, this is a Dutch mathematician, and so if somebody here Dutch can pronounce this guy's name for me. So at the end, that's in any case auf Deutsch is his house, or auf English in English house. Maybe nine house, this part in here I'm almost sure about because I know other names like the Rijksmuseum and so on. That should be not something like nine. I think it's nine Hus maybe. So it's a condition which looks very heavy, even on later. So you see, it's a very strong condition. So to have coordinates giving you the complex structure is a very strong condition. This is called the complex Frobenius theorem. And was proved not so long ago by a person whom I don't know, but jointly with a person I know very well and I admire greatly, named Louis Nierenberg, and his co-author in this paper is named Rulander. It is a question of finding coordinates. You give me J and I've got to find the coordinates. This is solving a very heavy PDE. Again, this guy's in PDEs, he's interested in PDEs. This is a serious PDE here. Yeah, you give me an almost complex structure, that's on the tangent bundle level, that's infinitesimal. And I'm supposed to find coordinates, which is somehow global, nearby, that give you that almost complex structure. I see the question been moving.
My question was about the coordinates. Are they global or are they local?
Everything local coordinates.
Okay, so local.
In arbitrarily small neighborhoods of, given a point, so the question, let me state it precisely. Given a point, is there a neighborhood of that point, which are coordinates for a complex manifold with coordinates z1 through zn, so that j that you get from the coordinates is the j somebody gave you?
But aren't there always coordinates?
No, that's exactly the point. I'm trying to say it 100 times. I'm glad you're beating me to death. But there are coordinates, there are always holomorphic coordinates on a complex manifold. That's okay. But now I'm giving you an almost complex manifold. I'm giving you J, which is a bundle endomorphism. It's only defined on the tangent level. Okay? I don't have X and I don't have Y. I just have it defined on each tangent space, J squared equal minus the identity. That is not coming from coordinates. Right? And then I ask the question, can I find coordinates to give that? That's a wicked question. That's why I call it a mega result. This result is called the complex Frobenius theorem. The real Frobenius theorem is the triviality. The complex Frobenius theorem is a highly non-trivial result, but nowadays not, but at the time of Louis Nirenberg's proof, it was. Okay? Not so long ago. Okay, and you see the condition. Look at the condition, it's serious. If and only if. Okay. Okay. Definition. If omega m is symplectic, and J is a complex structure on M, which is defined by coordinates, so in some sense, a very friendly complex structure, and which is omega tang, then, well, I'll write it all out. Mj omega is called a complex okay, now. Okay.
Okay, well, can you just make sure that I'm very clear? What do you mean by defined by coordinate?
Okay. So let's go slowly. Yeah, it's a new notion for all of us. So let me go slowly against you ask questions. There's some vagueness here. I give you, or you give me, a bundle endomorphism of the tangent bundle. Okay? I call it J. That means, fiber-wise in the tangent bundle, J squared equals the minus the identity. Maybe we call that a complex structure at the infinitesimal level, because that's at the tangent level. Now, it would be wonderful if the manifold was complex. If the manifold is complex,
The manifold down.
the manifold downstairs, very good. The manifold downstairs is complex. it might have coordinates z1, z2, z3, and so on, holomorphic coordinates. That means you have z1 equals x1 plus I, y1, and so on. That means you can define a map, j of ddxi is equal to j of d is equal to ddyi, so multiply that rotation, and j of ddyi is minus ddxi. Okay. That is the complex structure that came from the complex coordinates. Right. Question: given a complex structure on the tangent bundle, are the coordinates that give it?
See, again, it's not always the case.
Let me tell you how much it's not the case, and that's the point that Gromov is making here. First of all, here's the condition. I don't know, it's hard to understand the condition. Okay. Second of all, as an example, if M is compact, say, okay, the space of all complex manifold structures on this, in the sense of coordinates, is certainly finite dimensional with some, it's finite dimensional. Just take my word for it. This can be made precise. Okay. The space of all of these infinitesimal coordinate things is hugely infinite dimensional. Okay? Okay? And that was somehow Gromov's point. You free yourself up from all of this rigid coordinate stuff, and you have the availability of doing more, introducing more technology. Okay? That was his idea in some sense. Okay? We all right with that? So a Kähler manifold is such a manifold. It's good. The complex structure comes from coordinates. It's a complex manifold. Now I'm running out of time today, and I don't want to put you through. Oh no, we should. I'll have a little bit more time, I think. Okay. Let me just say, every complex manifold you will think of is Kähler. Now that's a terrible statement, but I challenge you to give me a non-Kähler manifold. Yeah. Well, I can do it. I'm a specialist. But okay, but you'll have a tough time. Okay. Here we go. Complex projective space is not only Kähler, it's projective algebraic. It's much better than Kähler. It's a Kähler manifold. Okay. I will produce for you the Kähler form. I have to produce a 2 form. Okay. I will produce it for you. Complex submanifolds of a Kähler manifold are Kähler. This is the wonderful thing. The restriction of a symplectic manifold to a submanifold may not be symplectic. It may vanish completely. We know that, right? The restriction of a Kählerian form to a complex submanifold, well, you can check it. It will always again be Kähler. That means any submanifold, a projective space, is Kähler. That means the entire subject of algebraic geometry is Kähler. Okay? It means that that's the first part of my challenge. You will have a very tough time thinking of something that's not algebraic, and every algebraic thing is Kähler. Every torus is Kähler. They're not all algebraic, but every torus is Kähler. Okay. I can give you a complex manifold just for fun to make sure you have one in your pocket which is complex and is not Kähler. And maybe I'll do that for you right now, just so you have an example of a complex manifold which is not Kähler. Okay? It's very hard. I'll give you one, but my colleague Kevin will be happy about this because he likes things like this. What do you want?
Yeah. So you say the restriction of omega into any submanifold is going to make it Kähler.
If the submanifold is complex, the restriction of omega to that manifold is
Okay, so,
Taylor.
right. So when we say, so omega is a symplectic form,
That's right.
complex symplectic form,
No,
not real.
no, it is a real, honest to God, symplectic form from, it is not, it is real valued, it is a real symplectic form.
Okay,
So when we're talking about this, I'm talking about projective space, for example, as a real manifold.
right, so I'm thinking, what if the submanifold is odd dimensional?
What?
If the submanifold is odd dimensional, but then
No, it's a complex manifold.
it should be even. Right?
It will automatically be even. That's the first remark.
Okay.
That's the problem with restriction. One, this is the first sort of nice obstruction. In the symplectic case, you restrict to an odd thing, you're in trouble. Right? But you restrict to a lot of even things, you're still in trouble. But here, if you restrict to a complex thing, you're not in trouble. It's still Kähler. And you can just check it. The definition, it's just immediate from the definitions. Okay? And it's wonderful because you then suddenly have a huge situation which is clear. So let me give you an example, and this example actually has a physics name on it, but no physicist thinks about it the way complex analysts think of it. So, N is a complex manifold, is G modulo gamma, so a group modulo a discrete group. G is the group of upper triangular matrices with unipotent matrices. Complex unipotent matrices. So as a manifold, it's just isomorphic to C3 as a manifold, but as a group, of course, it's not abelian. And of course, here I mean the ZI's are complex numbers. So your first non-abelian group that you should look at is this one. Maybe it's your second, I don't know, but this is a non-abelian group. These matrices do not commute. And gamma is the subgroup defined by just the fact that the ZI's are in Gaussian integers. So Gaussian integers means Z, a Gaussian integer, Z is a Gaussian integer. I don't know if you're familiar with this notation. It means Z equal to M plus IM, where N and M are integers. Okay? Okay? Now, this is very close to a torus. You see, a torus is C3 modulo a lattice of rank 6. Right? 6 directions in C3. This thing is C3 modulo a discrete group of rank 6 because each of these have 2 degrees of freedom in the Gaussian integer, but non-abelian. And this non-abelian phenomena leads to this manifold is not Kähler. It is complex, it is not Kähler. And it is compact, and so on. So there are such examples. There are many such examples. If you're interested, I know many others. I want to comment because of Sandeep, because he's interested in partial differential equations. I know that, right? As a last remark, if M is complex in the sense of coordinates, with coordinates, then holomorphic is defined by the Cauchy-Riemann equation. Is defined by the Cauchy-Riemann equation. Okay? You've heard about these Cauchy-Riemann equations. Let me write them over the reals. And so if F is equal to U plus IV, then the Cauchy-Riemann equation is something like Ux equals Vy and Uy equals minus Vx. And of course, in many dimensions, it's more or less the same. That is one of the most stupid systems of partial differential equations you can write down. You couldn't think of anything simpler, right? This is a system of linear PDEs. It's a linear system of PDEs. Right? Very simple system. This is very much related to the Laplacian, the Laplace operator, which is also the linear Laplace operator in these coordinates. It's almost the same thing as the real and imaginary part being harmonic. So it is very, very interesting from the point of view of linear PDEs. Okay? We write this system of equations as d bar f equals 0. We call this the dr, then we write that way, that's what that means. Right? It's the so-called d bar equation. Now this is dedicated on this a little bit to Sandeep. If the structure does not come from coordinates, the d bar equation is nonlinear. Okay? It goes into another world. Okay? If this thing does not come from, you still have the notion of holomorphic. Right? It is a nonlinear PDE system. Gromov had the courage to use this nonlinear PDE with this theory. So it looks really wonderful. You have a symplectic manifold, you have an almost complex structure, you have the notion of holomorphic, but suddenly you want to know what the hell that means, and it means d bar equals 0, and this is a horrible PDE. Okay? So you can imagine, you have experience with just linear Mickey Mouse PDEs and nonlinear PDEs, and it's another world, right? It's another world. And that's what's really going on here. And Gromov introduced these things, and it's become a beautiful, important theory. So I thank you very much for the lecture, coming to the lectures today. I enjoy it because I enjoy this mathematics very much. And we'll meet next Thursday. And don't worry about homework. Try to find something interesting I want to ask about. And two kinds: curiosities and technical stuff that you really need to know to understand better my lectures.
Yes. So there's this limitation, I don't know, some people have been just ignoring it, of having only one page. Sometimes we need to go slightly over a page.
That's great. Do what you want. If you wrote 100 pages, I wouldn't read it. But if you wrote only a half a paragraph, I would not be happy. But if you write a page or so, or 2 pages, whatever, you know. Okay. I want to make sure everybody. I've talked to Maria a little bit about you've got to be a little bit better in tech, maybe. I guess everybody else here is just fine in tech. Good, that's good. Because I like to make the comments on the tech file.